Resources on the 10 series GPU architecture. On the 10 series architecture, 240 thread processors execute kernel threads. These processors are grouped into 30 multiprocessors, with each multiprocessor containing 8 thread processors, 1 double precision unit, and shared memory, which allows thread cooperation. Each multiprocessor performs computations in SIMT, or single instruction multiple thread fashion. SIMT is similar to SIMD, or single instruction multiple data, except that SIMT is a bit more flexible in that each thread is executed independently with its own instruction address and register state. SIMT enables programmers to write thread-level parallel code for independent scalar threads, as well as data parallel code for coordinated threads. CUDA kernel threads have access to a variety of memory spaces which differ in scope, size, lifetime, and latency. Each thread has read and write access to per-thread register memory, which is on-chip and exists for the lifetime of the thread. In the 10 series architecture, there are 16,384 32-bit registers per multiprocessor, which are divided amongst threads in all resident thread blocks. Unqualified variables that do not fit in registers reside in local memory, which is uncached in DRAM. The lifetime of both register and local memory is the lifetime of the thread. All threads within a block have read and write access to fast on-chip shared memory. In both 8 and 10 series architectures, 16 kilobytes of shared memory are divided between all resident blocks on a multiprocessor. The lifetime of shared memory is the lifetime of the block. All threads have read and write access to the same global memory, which is located in the device DRAM. Global memory is large, up to 4 gigabytes, uncached, and exists for the lifetime of the application so that it is persistent across kernel launches. In addition to kernel thread access to global memory, the host has read and write access to global memory. As such, global memory is used to transfer data between the host and device for kernel input and output. The kernel memory access on this slide is a depiction of the memory access for programming abstractions such as threads, blocks, and kernels. It is useful to complement this depiction with a physical layout of these memory spaces. The physical layout of various memories is shown on this slide. On the chip, we have the fast register and shared memories. In device DRAM are the local and global memories. Local memory is local in scope. It is local to a thread, but physically it resides in the device DRAM. From a performance perspective, one wants to leverage register and shared memory in order to minimize use of local and global memory. One should note that data transfers to and from the host go through global memory only. An application cannot read or write to shared memory directly. The execution model for CUDA, starting at the smallest scale, is that threads are executed by thread processors. Thread blocks are executed on multiprocessors. Each thread block, once assigned to a multiprocessor, does not migrate. Several blocks can reside concurrently on a multiprocessor, which is desirable from an efficiency standpoint as thread switching is used to hide memory latencies. The number of blocks that can concurrently reside on a multiprocessor is limited, however, by the multiprocessor shared resources, namely the number of registers amongst all resident threads and the amount of shared memory partitioned between all resident thread blocks. Kernels are launched as a grid of thread blocks, where only one kernel executes on a device at a time. CUDA advantages over legacy GPU, where generic computing operations are mapped onto the graphics pipeline. In CUDA, memory access is much more flexible than GPU. Threads can access any memory location as often as needed. CUDA threads can cooperate within blocks through shared memory and thread synchronization. Significant bandwidth reduction to device memory can be achieved when threads in a block cooperatively load data into shared memory, where any thread in the block can access any shared memory location. Another advantage CUDA has over legacy GPU is that CUDA has a low learning curve. CUDA consists of a few extensions of the C programming language and no knowledge of a graphics API is required. CUDA does not just hide the programmer from a graphics API, but has been designed in both software and hardware to perform a different route to the computational resources, thus avoiding the performance penalty that would be realized if it were simply a software layer that sat on top of the graphics layer. In summary, there are several key abstractions in CUDA which allow a programmer to easily and efficiently harness the computational power of GPUs for non-graphics applications. The first abstraction is that CUDA makes use of many lightweight threads. Over 1 trillion threads can be launched in a CUDA kernel. The negligible overhead associated with thread creation and switching permits the granularity of parallelism to be very small without impacting performance. This results in a very simple data decomposition model. A unique thread ID is used to access array elements and perform computations on these elements. CUDA has a simple 2-level hierarchy of concurrent threads. Threads are batched together in blocks, where the independence of thread blocks gives the hardware great flexibility in scheduling threads and results in excellent scaling using this simple execution model. Within a block, threads have the ability to cooperate. Threads within a block can synchronize through a lightweight barrier synchronization. Threads can also share data and thus global memory accesses through per-block shared memory. This thread cooperation within a block provides simple synchronization and communication models.